13th lecture. Hopefully, it will turn out to be lucky. And we will continue on what we started last time, namely on deriving some kind of lower bounds on the linear decision tree model. Right. So, we started looking at this problem of element uniqueness, okay, and we are trying to parameterize. We parameterize the problem as, so if you consider an input of the given n elements as a point in a high n dimensional space in R to the n, and then we want to look at this space that is the Euclidean n dimensional space, where a point can be classified as yes or no depending on whether there is a duplicate element or more than one duplicate vis-a-vis where there are no duplicates. Okay. So, in 2 dimensions the space partitioning would look like, you have this 4 quadrants and you take this line with slope 45 degrees, and exactly the points on that line are those inputs. We are considering only 2 point inputs. The points in the line will be those that are not unique, because x1 is equal to x2. Okay. Any other point on either side of this line, okay, will comprise the yes answers. Okay. So, analogously, if you go to higher dimensions, okay, you can look at these pairwise the hyperplanes defined by this x I equal to x j, where I is not equal to j, and if the given input point lies on any of these planes, the union of these planes, then the answer is no, because there is at least one duplicate. Okay. And if the point lies outside of the union of these hyperplanes, then the answer is a yes answer. Okay. So, what we are actually doing is we are partitioning the input space, okay, into some kind of equivalence classes. Okay. So, in the very high dimensional space, so maybe even going from 2 to 3 may shed a little bit more light. So, when we go to 3 dimension space, okay, so fine. So, you have these planes, let us say, so you have right hand coordinate system. So, x, y, z, right. So, you look at, so this plane that I have just drawn is supposed to be 45 degrees passing through the origin, okay, and it is supposed to be what does it look like? Let us say it is y equal to z or something, okay, and you have 2 other planes where x equal to z and x equal to y. Okay. So, there are these whatever some 3 such planes, okay, and if you think about it, these 3 planes are not completely independent, in the sense that they are going to partition this R cube into actually 6 regions. Can you see why?
Each of them, when you start,
so yeah,
dividing first plane is dividing in 2 parts, then you add one more divided.
Right. So, then it divides into 4 parts, right, but then when I add the third one, it is not 8 parts. It is not 8 parts. See, the orthents, the planes x y plane, y z plane, they also do the same thing, right. The 3 orthogonal axes, they actually divide the space into 8 parts, but these 3 planes I claim divide only into 6 parts. And the reason is that y equal to z and x is equal to z, then by transitivity y must be equal to z. So, it is actually going to, the 2 planes intersect in a line, and the third plane has to pass through the line. So, it becomes 6 planes rather than 8 planes, and the other explanation is that in each of these 6 regions, okay, you have one of these 3 inequalities, right. So, depending on the permutation of, so let me use the well, I am using x, y, z. So, x, y, z, okay, can be permuted in 3 ways, right. 3 elements can be permuted in 3 ways. So, each region, okay, each region corresponds to the 3 factorial that equal to 6 orderings of 3 elements. Okay. So, this is in 3 dimensions. So, when you go to n dimension, we are talking about n dimension, the point is the given input is an n dimensional point. Okay, the input of n elements can be thought of a point in the n dimensions. Then essentially, the analogously in n dimensions, okay, there are how many such regions? N factorial, right? The each n factorial regions corresponding to each permutation, and each region is a yes or no. The regions is a yes answer, right, because there are no duplicate elements, right, corresponds to a yes answer. Okay. So, we have essentially these n factorial regions, and each region is kind of equivalent in the following way, that within a region, within these regions, the answer is a yes. Okay. Now, what have these regions got to do with an algorithm? Okay. This is purely in terms of the input and the problem. The problem is the element uniqueness problem, and whatever is the input to that problem. Right. At this point, this has got nothing to do with the algorithm. Okay. So, somehow we will have to bring in some way that we can relate the way the algorithm behaves and how it is able to actually answer this correctly, yes or no. Right. So, for that I need use some one, I will just exploit one basic property of the kind of algorithms we are looking at. Okay. The kind of algorithms we are looking at, again you recall, is in the linear decision tree model. Okay. We are not looking at fixed degree algebraic decision tree, we are not looking at arithmetic computation tree. Okay. As we discuss more, you will see why I am drawing the distinction. So, right now my primitives are linear inequalities. Okay. Linear inequality, is it greater than 0? Sorry, greater than or equal to 0, strictly less than 0. Okay. So, this is basically at any node of this decision tree, we are evaluating this and moving left or right depending on whether the answer is yes or no. Okay. Now, these kind of decision tree models has one important property, okay, and that is so linear an important observation about linear decision trees. Okay. So, and that is so given any point so this point is in n dimension. So, point let us say P in n dimension, we follow some path from the root to some leaf node. which corresponds to either a yes or a no. Okay. So, in other words, okay, this decision tree itself, whatever it is, some specific decision tree. So, any decision tree also implies a partitioning of the n dimensional space. Okay, in the following way. Right. That is, every node, whether it is leaf node or an internal node, okay, corresponds to some subset. Let us say call it any node, what should we call it, node, a node, let us call it T. Okay. So, every node T corresponds to some subset, call it W T, okay, of R sub n, namely all points that pass through T. Okay. So, whenever I have, so any decision tree based algorithm where the basic primitive is taking a linear inequality and just finding out that it is greater than or equal to 0 at any node. Whenever we reach a node, okay, so whichever points passes through that node, we say that this node is associated with that subset of R sub n, W of T I am calling it. So, eventually of course, the leaf nodes correspond to all those points in R to the power n that reaches that leaf node. Likewise, for any other internal node, any point that reaches that node, okay, corresponds to that particular node. Okay. So, that which I am calling it. So, W's of T corresponding to the node T. So, okay, let me draw a picture. So, here is my decision tree. Okay. Some point, let us say P1, there is some point P2, there is some point P3. Okay. So, when I start the algorithm with input P1, P1 traces some kind of route through this tree, right. So, this is let us say P1. Okay. P2, okay, maybe traces another route to the tree. Okay. This is P2. Okay. P3 could be like this. This is P3. Okay. Now, if you look at the path that P1 and P2 took, okay, they shared the same path till this node, okay, but then they went along different paths. Okay. So, the set of points that pass through this node, okay, and the set of points that pass through this node, okay, they basically define some kind of partitioning of the R to the power n. That is all I am saying. Okay. So, every decision tree also corresponds to some kind of partitioning of the R to the n. Not just for this particular problem, but for any problem, this decision tree will correspond to exactly those points that pass through those nodes. Okay. So, now we have two partitionings. One is the partitioning defined by a specific decision tree. Okay. Now, every decision tree will have its own way of partitioning. Okay. Your algorithm and my algorithm would be different. So, the decision tree corresponding to the two algorithms will be different, and they could imply different partitioning of the space. So, the partitioning is not unique. Right. So, but then we want to look at some properties of this partitioning, so that we can relate it to the problem. The problem that we are looking at is the element uniqueness. Element uniqueness has these n factorial equivalent regions that is defined. Okay. So, that is the property of the problem. Okay. this tree also defines some kind of partitioning. Now, there has to be some kind, if you are solving the problem of element uniqueness, then this decision tree that claims to solve the element uniqueness problem should also have some kind of correspondence with those with the partitioning of the problem space. Okay. In particular, the leaf nodes that this any decision tree has. Okay. So, suppose this is a leaf node yes, or maybe this is a no, okay, yes, no, whatever. So, this all these yes points, okay, must fall in those one of those n factorial regions, right. Yes must be in one of the n factorial regions, because those regions correspond to the yes inputs, okay, and these no must fall into one of those union of the hyperplanes. Okay. So, this must lie on some hyperplane. Okay. And the yes should lie in the regions, one of the n factorial regions. Okay. So, let us blow up this figure a little bit further. Okay. So, what we have now are some kind of partitioning of the problem space. Okay. So, problem space partitioning. Okay. So, what I am saying is these are my yes regions, okay, for this particular problem, these are my yes regions, okay, and the one that lies on this line, of course, this is not the correct representation of that particular problem, but it is an abstract diagram, and anything that lies on these hyperplanes, they are the no regions. Okay. There is a partitioning defined by the decision tree, okay, and a leaf node, okay, must have points. So, the leaf nodes will have points either that fall on the lines or in these regions. Okay. So, what can we say about the regions corresponding to a leaf node? So, can it have something like this? So, for instance, can the partitioning be like this? Can some leaf node basically be associated with all these points? This is the red partitioning is of the decision tree. So, can any single leaf node correspond to this shaded red region? What is the problem? Right. So, see, it seems to contain yes points and no points, which is completely ambiguous. Okay. So, clearly not permissible, okay, not possible. So, no single leaf node, okay, can span across two such regions, right. In other words, what we are saying is that a leaf node must necessarily be, okay, confined to, well, no, not necessarily. The single leaf node may correspond to this. All we are saying is that as long the leaf node has to be consistent, it cannot have both yes and no points, right. So, the leaf nodes, from what we just what we have observed till now, is that it has to be completely contained within this region. Okay. Maybe so the same leaf node, okay, maybe all of them belong to the same leaf node or same node or whatever. Particularly, we are arguing about the leaf node. Okay. Perhaps they all belong to the same leaf node, because all of them are yes answers. Okay. So, this is a plausible scenario. Now, actually we will prove, or what we will observe is that even this is not possible. So, that is what we will prove. Okay. Why is so? Why is it so that? So, we would like to actually now somehow argue that even this scenario is not possible, that is, a leaf node cannot be union of these regions coming from different. Okay, so since the word connected was used, I do not want to get into the definition of connected regions, but you can see what is meant by connected region here. So, this region is connected because I can go from any point in the region to another point in the region by staying completely within the region. That is all. Okay, I am not even saying straight line segments. I am just saying that as long as I can travel from this point to another point without going outside the region, it is a connected region. Okay. So, question is that can the leaf nodes comprise of union of subsets that lie in distinct connected regions? If not, okay, let us even set that aside. Suppose we manage to prove that a leaf node can have the region corresponding to a leaf node can be in exactly one connected region. What will that imply? Okay. Suppose, suppose each leaf node, the yes leaf node, the yes ones, okay, corresponds to points in at most one region. This implies number of leaf nodes is greater than n factorial, number of regions, right? Number of regions which is equal to n factorial, and then we are done actually. If you think about it, it is a binary tree, and if the number of leaf nodes exceeds n factorial, then you have the time of the or the height of the tree to be n log n, right, log of this quantity, then you are done basically. So, why is this true? So, this is the connecting link.
Any point on the line, on the no line, can be expressed as a linear combination of 2 points in disconnected components, and then since both these answers are yes, they are linear combinations.
Why? What is the property of the linear decision tree that we are using here? Okay. So, the only thing that we are using in the decision tree model is that every decision is a linear inequality. Okay. So, either it is this side or that side. So, the second property, okay. So, note, so let me highlight it, okay. Every node is associated with a convex region. This is the operative word, because it is the intersection of linear inequalities. Okay. Intersection which are convex sets, right. That is it. So, the primary property is this, the fact that every node and therefore, every leaf node is connected is associated with a convex region, and therefore, if there are a leaf node corresponds to two such regions, okay, it means that it must also contain any kind of linear combination, okay, that is namely the entire segment should lie within that leaf node, which means that this point should also lie on the leaf node, which is a contradiction, because the leaf node cannot, it must be unambiguous, it must be only yeses. So, there cannot be a no point associated with the yes leaf node. Okay. So, just from the convexity property it follows that that a leaf node can be associated with at most one region, and after that so overall if you try to capture this entire result, it basically amounts to the following, that the number of leaf nodes must exceed number of, so we will actually say the number of connected components. Solution space. So, the solution space has n factorial connected components.
So, every region has at least one leaf
I mean, so the entire space, so we are only arguing as in a like a greater than or equal to. So, every region may have more than one leaf node, but certainly the number of leaf nodes must be more than the number of regions. That is all we need. Okay, depends on what your algorithm is.
Every node T corresponding to some subset WT of particular every node, but is it every leaf node?
Including leaf nodes, right?
But I mean, maybe some intermediate node is.
Any node is corresponds to the intersection of inequalities, which is a convex region. Any node, including leaf nodes, right? So, the number of leaf nodes must exceed the number of connected components of the solution space, okay, which means that the running time or the height of this decision tree, sorry, linear decision tree, okay, is omega of log of number of connected components of solution space where So, this is the summary of what we just observed. So, therefore, as a corollary, your any linear decision tree based algorithm for element uniqueness has at least n log n L log n comparisons, or the linear inequalities. It computes at least so many linear inequalities. Okay, so far so fine, but someone comes up and tells me, oh sir, we don't need to compute any linear inequalities. Okay, I will just solve the problem, okay, in the following way. So, what is this? Okay, equal to 0 if and only if answer is how many? Forget about n square. Does it compute any linear inequalities at all? Does it fit our model of linear decision tree model? No. Okay. So, it completely falls apart, right? Is basically in that model it has no lower bound, because I am not even using even a single linear inequality. Right? N square is number of. So, moment I say this is a model of computation, I am only counting those operations. I am not accounting for anything else. When you talk about comparisons, when you sort, you only count comparisons, n log n comparisons. Okay, someone comes and say no comparisons, I just do hashing. That model completely falls apart. Okay, so we will have to then somehow design a proper lower bound argument for that model. Okay, so this is one possible algorithm, okay, which does not use any linear decisions, so no inequalities. Okay, and that it completely beats that model. So 0 essentially, because the moment we decide to use something else, okay, then this falls apart.
So this actually computes some polynomial of higher degree, right?
Whatever, right, exactly. So this is precisely the reason why proving lower bounds on the linear decision tree model, okay, may not be adequate. Okay, you would like to actually prove lower bounds using more realistic operations. Okay, so that is why last time I mentioned these words, or even today I mentioned them. What about higher degree polynomials? Okay, the moment you go to higher degree polynomials, there is a complication. Okay, I will just give you one example. So, if I have okay. So, suppose I have something like I just draw it geometrically, okay, rather than writing anything algebraically, but essentially it comes from something like this, So, do you remember this kind of equations? What is it? Ellipse, right? So, you have some kind of an ellipse, okay, and this essentially says that this is the region we are talking about, okay, and if you say greater than something, then it will be talking about these regions. Right. So, now and this is a degree 2 equation, it is just degree 2 equation. So, if you take intersection of two degree 2 equations, okay, you could end up, so I have taken ellipse like this and take an ellipse like this, I take one greater than, one less than, I have now the intersection can be not one connected component. Okay. So, the moment I go beyond degree 1, okay, I can't say that the intersection of two such inequalities, higher degree polynomial inequalities, is one connected region. So, this kind of argument does not hold anymore, that whatever corresponds to a leaf node must lie within a single region. I could have actually for the same leaf node actually things spread across, okay, and then I can't claim that the number of leaf nodes must exceed the number of the connected regions of the solution space.
But so you came to this conclusion only because you started with some convex partitioning, because you're saying your inequality actually gives you convex sets.
Right.
But here you actually don't do that, right?
Right. So, precisely. So, that is what I am saying. So, the linear inequalities was a very special case. Okay. It went beyond comparisons, but it does not go far enough to deal with higher degrees. So, the the non-convex sets essentially. Okay. So, and it is true that you can actually go ahead and use higher degree equations, inequalities in your algorithm. No one is stopping you from doing that. That is completely realistic. So, we can't use that simplistic argument. Well, I mean, not as simple as what we did now, but people have been able to extend these bounds, and I won't talk about it today. So, see, the solution space partitioning remains the same. That is completely problem dependent. It is the kind of decision trees that correspond to a certain kind of primitive. So, the moment I increase the degree of this primitive, okay, then I can't use that simple counting thing. Okay. But then what people have managed to do is that there is a relation between, okay, so there is some kind of relation between degree of inequalities, okay, and the number of connected components corresponding to a node. Okay. So, this relation, this comes from some fairly deep theorems in algebraic topology, okay, and the one that we could have discussed, but it's no point just telling you about a particular bound, but I'll mention it. It follows from, at least historically, it follows from what is called Milnor-Thom equations. Okay. So, Milnor-Thom bounds, they give you some kind of handle on the number of connected components related. So, if suppose I could say that if the degree is 2, the number of connected component is 2, then more or less what we said would hold, but it is not that simple. Okay. It kind of grows exponentially with dimensions. Okay. So, then one had to sort of refine these arguments, and finally, by the way, the same kind of bounds hold, that for element uniqueness problem, the height of the even a higher degree algebraic decision tree is roughly about log of the number of connected components of the solution space. Right. So, it requires some more careful counting, some more careful argument, and use of these things called Milnor-Thom equations. Right. So, if you are interested, I could give you a reference. In fact, it is there. If you have a copy of the Preparata Shamos book, it even has that formula, but I do not want to just throw a formula that will not make sense. Right? The formula itself is not very complicated. Okay. So, I will just limit my discussion on lower bounds to essentially linear decision tree models with some idea that essentially it is a counting of the number of connected components with a leaf node. That is that is the central thing to get a bound, okay, and that can be done using some more so fairly deep equations. Okay, so that is one part of the lower bound, and this lower bound is for element uniqueness, and therefore, the same lower bound also holds for what other problem? At least sorting. Yeah. So, we could reduce element uniqueness to sorting. So, even if you are told that I just posed that problem, right, instead of comparison I am allowed to use more powerful primitives like x1 minus x2 plus x3 something like that is greater than or equal to 0. So, even with that restriction even with that flexibility, you will still get an n log n bound on sorting. Okay. What really kills sorting is moment you allow things like indirect addressing. Okay. Okay, the next application of this bound will be to this convex hull thing that I have been promising. Okay. So, let us look at the reopen convex hulls. Okay. So, the lower bound that I derived for convex hulls was connected was related to sorting, that if I want the points to be in the convex hull to be output in sorted order, okay, then sorting can be reduced to convex hulls, okay, and therefore, the lower bound for sorting applies to convex hulls. But it is a kind of a weak lower bound. Someone could say that, okay, I am not interested in looking at the ordered output of the convex hull. I will be happy if you can tell me. Okay, so for convex hulls, okay, a relaxed version can be just enumerate in any order. So, I am not imposing any kind of sorted order the corner points. Okay. So, this could be one version. Okay. Another version could be since we are more comfortable about lower bounds for decision problems, let us make it a decision problem. Okay. Given n points, do all points appear on the convex hull? This is certainly a decision version, right? A decision problem. The one that we will actually pick up and which will also address this number 2 is where we will also somehow incorporate the notion of output, because I have been telling you that this input and output together, we have an algorithm that combines both inputs and outputs, right. So, the problem that actually that I will take up is the following. So, version of convex hull that takes so that version will be as follows. Given a set of n. So, we talk about 2-dimensional convex hulls. So, if you can get a lower bound on 2-dimensional convex hulls, it automatically implies lower bounds for higher dimensional convex hulls also, right. where when you say h points, exactly h points. Huh? So, I give you this input set and give you some number 100. Tell me whether there are exactly 100 points on the convex R. Okay. Some number, and that number must be less than n, because there can be at most n points in the convex R. In fact, it should be between 3 and n, because it has to be at least 3. So, for this problem, what I will devise is a special case of this problem. Okay. So, let us call this problem P 1, and then we will talk about a special case P 2, and P 2 looks like this. I have so this is a regular H cone. Okay. And this is the circumscribing circle of the H cone. Okay. I will also have similarly so this is my inscribing circle. Suppose this is the center of the circle. Okay, so what I have is a regular H cone, which means that all these internal angles are same and all these edges are of same length. And I am not going into arguments where you can draw a regular H cone for any H. Okay. So, and then I consider the circumscribing circle and I consider the inscribing circle. Okay. So, I did not draw it very well. So, there is a touching point basically everywhere. Sorry, it is exactly one touching point. So, this structure essentially looks like, there are these wedges. Okay. This is the shaded region, and the shaded regions have no connections between them. That is, if I can't, well, I mean, let me define what I mean by no connection. So, if you consider that I want to travel from, let us say, one shaded region to another shaded region. Okay, so, can we go from one shaded wedge to another, okay, without traveling out of the. So, let us call the circumscribing circle as C I, inscribing circle as, well, no, sorry, C C and C I. Inscribing circle is called C I and the circumscribing circle is called C C. So, can we go from one shaded wedge to another without traveling outside of C C and inside of C I? That is the question I am asking. So, if I want to travel from this red point here, okay, and I want to, let us say, go to the adjoining one. Okay. So, my path, okay, so either I will be sorry, okay, no, please, I retract this, just a moment. One shaded wedge to another without traveling out of, no, not just outside of CC. I should actually also bring into the picture the no, not the boundary points. I should okay, let me not, I'll make it even simpler, sorry. Can we go from one shaded wedge to another wedge? To another using a path that completely stays within the wedge. In the shaded region. Okay. The shaded region cannot include these points, the points of contact. Essentially, what we are saying, I am saying that these are disconnected, right. I cannot go from one wedge to another. If I try to go there, so I'll have to sort of either whatever I do, I take this path, either I am going to cross into the inscribing circle, okay, or I am going to come out here, okay, outside of this H con. Okay. So, or yeah, essentially I am going to go out of the H con, or I am going to go inside the inscribing circle. Okay. So, then what has all this got to do with lower bounds? So, the special case P 2 that I am trying to pose is the following, that we are given actually the points of the. So, the early P 1 was that given any set of n points and some number h, are there h points on the convex hull. Now, I am actually fixing these h points. Okay. So, fix the P 2 is fix the h points to be the regular H con, okay, and the remaining n minus h points are chosen arbitrarily. Okay, in the region, in the annular region between C inscribing and C circumscribing. Okay. So, these h points are fixed 1, 2, 3, 4, 5 h. The remaining points, okay, have to lie, it cannot lie within this inscribing circle, not allowed, it is not allowed to be outside of the circumscribing circle. Okay. It has to lie basically in this annular region, the small ring between the inscribing and the circumscribing circle. So, this is how I am defining my input. Okay. And then I ask the same question. Then we ask the same question, are there h points on the convex hull. Okay. So, this is my problem, the new problem. Okay. Claim is P2, the second version of problem, is easily reducible to my original problem. Why? P2 only says these h points have to be on the h con, sorry, the vertices of the h con, okay, and the remaining points should be in that annular region, which means basically that I take every point and see whether it is inside the it is outside the inscribing circle and inside the circumscribing circle. Okay. So, it is just two tests, two inequalities that I have to test. Right. So, in linear time I can reduce problem P2 to P1. Okay. If I can solve P1, I can solve P2, because the only thing I have to make sure is that every point must lie in the annular region, which is just a linear time test every time. Okay. So, which implies that lower bound of P2 is a lower bound for P1, because P2 is reducible to P1. So, how do I get to a lower bound of P2? Why is it easier for us to get a lower bound for P2? See, the n minus h points, if there has to be exactly h points on the boundary. So, now I am going to count the number of connected components somehow. Okay. So, you know that in the solution space, if there is a certain number of connected components, we know that the height of the decision tree must be at least log of the number of connected components. Okay. So, h points are fixed. The remaining n minus h points, okay, must lie in one of these wedges, because if it is a point lies outside the wedge, there has to be more than h points on the convex hull. Okay. So, between two yes configurations, this is essentially a distribution of these n minus h points. So, n minus h points have to be distributed to the h wedges. How many ways can you do that? Right. So, h to the power n minus h. Okay. Now, I claim that between, so any of these two yes instances, okay, they must be in different connected components of the solution space. So, now the solution space is in this high dimensional space, you know. So, high dimensional space here is we have n points, each point has 2 coordinates. So, we are talking about r to the power 2n dimensional space. Okay. In that space, I am trying to sort of visualize what are the connected components of the yes regions. Okay. And I claim that the number of connected components is h to the power n minus h. Why? Because to go from any yes instance to another yes instance, okay, you have to necessarily go through a no instance. There is no path that connects to wedge without going outside of the solution. I have to either cross inside or I have to go outside. So, there is no way, I cannot draw a path in that region where I travel from this point to this point without crossing some kind of whatever separating boundary, which is a no solution. There is no path, and therefore, when I, so that is basically what this figure, I mean the this is a 2-dimensional projection of that actually. So, I cannot go, because if I try to go in this, if it is not connected in the 2-dimensional picture. So, it cannot be connected in that higher dimensional picture. Okay. And log of this, which means that, and log of h to the power n minus h is n minus h log h, that is the lower bound. Okay. So, just think about it, and if you have any questions, we can take it up later on. Otherwise, this is the end of the story for lower bounds. I mean, I am not going to go any further into lower bounds.